Okay, so next up, we have Howard Wu speaking all about Aleo.
Hi everyone, my name is Howard Wu. I'm a co-founder of Aleo, a platform for fully private applications. I wanted to start by thanking Anna for hosting the Zero Knowledge Summit and the sponsors for making this event possible. In this talk, I'd like to explain the concept of Aleo, where the technology stands today, what it enables, and how to get involved as a developer and/or cryptographer. So to get started, I thought I could share a bit about my background in blockchains and the ZK ecosystem, and frame the notable accomplishments and shortcomings of the space. My journey began, like so many, in Bitcoin. For myself, I was into computers at an early age, and during my high school years, I came across Bitcoin just as it was getting started. And while I had little experience with the technology at the time, I did have a fascination for the mission, the incentives, and the value propositions of the cryptocurrency. And like so many, I began mining Bitcoin in order to support the effort. Fast forward to 2014, and the concept of a decentralized world computer began picking up steam. And I found myself shifting my interest from pursuing endeavors like Bitcoin scripting to programming on blockchains like Ethereum. Unlike Bitcoin, Ethereum offered a far better developer experience and allowed programmers to write financial logic to dictate how cryptocurrencies were transferred. And it was around this time that I was in university now and began pursuing research in cryptography under two professors. One was Professor Alessandro Chiesa, who himself is a co-founder of Zcash, and also Don Song, who is a co-founder of Oasis Labs. Along with several others, many in Alessandro's lab, we saw the work of zero-knowledge proofs mature into the genesis of Zcash, a fully private cryptocurrency. And unlike Bitcoin, Zcash offered privacy for payments and spurred the awareness of on-chain privacy as a concept. Unbeknownst to most of us at the time, the implications of this work continues to have long-standing implications for how and where cryptocurrencies can be adopted and used. So about 3 years ago, a few of us began evaluating the blockchain landscape along two dimensions, notably programmability and privacy. We realized that Bitcoin offered low programmability and low privacy. Ethereum extended Bitcoin in one direction to offer high programmability, and Zcash went the other direction to offer high privacy. However, there was an upper right-hand quadrant of high programmability and high privacy that remained missing in the landscape. And we decided to tackle that with a protocol that we developed called ZEXI. We designed and published ZEXI, which stands for Zero Knowledge Executions, as a protocol for decentralized private computations, and it's a cryptographic protocol that enables both privacy like Zcash and programmability like Ethereum. ZEXI is a ledger-based system that allows users to execute offline computations and produce publicly verifiable transactions on-chain, which attest to the validity of those offline executions. ZEXI's two-part architecture introduces the split between off-chain and on-chain verification, and every application using ZEXI goes through both on and off-chain phases. In the case of an application that's being submitted on-chain, miners on-chain act as verifiers that serve to validate the actions of the application and to ensure that they are truthful. By having the verifier on-chain, we allow the network to process a large number of transactions quickly without hitting bottlenecks. Not only does this allow for high throughput with lots of applications running simultaneously, but it also enables applications of unbounded size to be supported and run on such a network. And the verification with each transaction takes just milliseconds on-chain, no matter the size of the application. So with ZEXI, we not only provide data privacy and functional privacy, but also leverage this to increase the scaling throughput and support unbounded computation size. Since publishing this work, a number of us who worked on ZEXI received a lot of inbound requests from dApps, token wallets, and DeFi protocols asking us to productionize the system. And I'm excited to say that in the past year, along with colleagues who worked on ZEXI, we decided to take this work into production as Aleo. Aleo is a platform for fully private applications, and Aleo is architected as a blockchain that is private by default, open source, and built for the web. Unlike existing solutions that seek to replace the web, Aleo is designed to integrate with it. For users, Aleo introduces new services that are both personal and private. And for developers, Aleo introduces a programming model that can easily integrate with existing decentralized applications. And so I'd like to walk you through how this model works. With this programming model, we really can break it down into effectively this diagram that you see here. The idea is for developers to write their applications in Leo, to then run it on provers, and those provers publish the results as transactions on a blockchain. And to break it down more concretely, in the first step, users can write their applications in this programming language that we have developed called Leo. Developers will write and define user actions in the language, which then gets compiled as an application and can be packaged and in a collaborative environment for you and your team. Second, on provers, developers can host their applications as a package, as a web application. And with every one of these applications, they can process and execute and facilitate interactions with other users across the web. Lastly, as it's open and it's part of a global network, this is also something that can be easily controlled or managed, but also accessible to others around the world. And because there is a blockchain that is checkpointing and storing the state of everything, we also have finality. And the nice thing about this architecture of finalizing it on Aleo is that the transactions themselves can be submitted anonymously. But in addition, because we use this ZEXI architecture to process transactions, every transaction itself can be verified very succinctly. And lastly, we can store your records on there permanently. On Aleo, every transaction encompasses records themselves that are fully private. They're encrypted under the receiving address's public key, and this ensures that no matter how you store your data on chain, it will always be private by default. If an application wishes to make that public, they can publish the view key either for the record or for the entire account as part of the memo field in a transaction, and that gets broadcast and becomes visible by everybody on the network. What we're really talking about when we talk about Aleo, however, is this idea of programmable zero knowledge. Programmable zero knowledge combines both the development opportunities of a programmable protocol with the privacy and security of a zero knowledge protocol, powered by ZEXI in this case. The result is a solution that both developers and end users want and can use. Dark pools and mixers have been the primary applications leveraged by users of Tornado Cash and Zcash. Providing that degree of transaction privacy has driven extraordinary success. People recognize the need for more natively private ways to transfer value and have migrated funds to platforms that can support that value proposition. So I believe that the appetite for privacy is obvious, but core to that value proposition is privacy as native. Most prominent layer 1 blockchains are addressing privacy concerns to some degree, but they are doing so mostly through layer 2 solutions. Though these layer 2 innovations will result in degrees of privacy being added to these protocols, privacy at the end of the day will remain a feature and not a core component. With programmable zero knowledge, Aleo gives developers the ability to build with privacy already baked in, and gives end users the confidence that privacy is not a voluntary add-on by the developer, but is rather an architectural bedrock of the underlying platform. Our first step towards opening up Aleo to the community has been as part of our mission in building out the Developer Preview 1. Developer Preview 1 is the first step towards launching the Aleo platform, and it is composed of 4 main components: SnarkOS, which is a decentralized operating system for private applications; testnet 1, which is a trusted testnet launched on SnarkOS to allow developers to begin writing and deploying applications; Aleo Explorer, which is a block explorer for the testnet and exposes RPC APIs and REST API endpoints; and lastly, of course, is the Leo programming language, a functional statically typed programming language for writing private applications. I want to spend a bit of time talking about SnarkOS and Leo, as they're components that make Aleo's solution particularly unique. SnarkOS is a decentralized operating system for private web applications, and it forms the backbone of Aleo and enables developers to checkpoint and finalize application state in a publicly verifiable manner. It runs a blockchain and supports all sorts of applications, so it's very similar to ones that people know and love on Ethereum. The idea for us is to use SnarkOS as the foundation or the backbone of this entire system. So SnarkOS is meant to checkpoint, verify, and store data in state. Leo is the programming language developers use to build on Aleo, and it looks and feels just like a traditional programming language. Yet under the hood, it is far more complex. Leo abstracts low-level cryptographic concepts and makes it easy to integrate private applications into your stack. Leo mimics JavaScript's approach, since it's a good paradigm for thinking about circuits, and JavaScript developers expect all code to either render or print to the console. Likewise, circuits will either render or compile to a circuit, and there is a clear divide between whether something should be asserted at proving time or compile time. Current languages for writing snark circuits don't have a clear distinction, and it leads to a lot of confusion. Instead, Aleo introduces a new syntax in order to elucidate the snark circuit logic. And to make it simple to bundle and share your work, we have built a package manager for Leo called Aleo Package Manager. Aleo Package Manager is the first package manager for zero-knowledge circuits, and it includes collaborative features like teams and organizations to make it easy to work with others on private applications. Our team's decision to incorporate a package manager, frankly, is just another key benefit to using Leo. And so we're asking for 2 things from the community today. The first, we're looking for open source developers to contribute to the development of SnarkOS and Leo. But second, we're also looking for feedback from the community on our design decisions, especially as we ready ourselves for a production launch. And if you'd like to get involved, I'd ask that you head to aleo.org to start programming or exploring Aleo packages.
Okay, and now here we are with Howard, and we get to talk a little bit more about this presentation. If you do have questions, please leave them in the chat. But I have a question that I thought could actually start this off. In this presentation, you didn't really talk exactly about like the cryptography like behind an actual transaction. Maybe you can walk us through what that would look like on Aleo.
Sure, I'd be happy to. Basically, there's a few circuits that we've been architecting, which are an evolution from ZEXI. Effectively, in the ZEXI architecture, there is what we call an inner and an outer circuit. The inner circuit itself, in our case, checks value conservation, but then also checks the validity of every record in the transaction that is being spent and also being produced. So, for example, If you have a record that you're spending, you want to make sure that the serial number hasn't been spent before. And on the other side, with a new record, you want to make sure that the commitments that you're now committing this record for also have not appeared on the Merkle tree, the global state of the ledger before. And so that's one circuit here that is used for value conservation and for validity checks. There is another circuit called the outer circuit here, which is it's more like a compression, but it's a little bit into that recursive proof composition that I was mentioning just previously. And the idea there is that not only can we compress state about the programs that are being run under the hood, but we can also ensure that this transaction itself is valid within a shielded pool that is not fragmented. And I think that that's a very nice concept here that is quite new in the fact that we haven't seen a production system do that today. And the third area is a circuit that we call the proof of succinct work circuit, and it's a circuit for consensus. And in this case, it allows us to effectively grind snarks, similar to doing proof of work in Bitcoin. We're now grinding snarks, and by doing this, the push has been really to drive a huge incentive for miners to actually invest resources and technology towards advancing, proving capabilities in hardware for snarks. And so by having a hardware accelerated snark, and mining this, that it actually gives you a really nice incentive for, earning rewards. But then in our case, designing it this way also allows us to incentivize and speed up the programs that people would run and build. And by doing it this way, I guess I should also mention that the proof system and the curves in the POSW circuit are the same as the curve and the proof system in programs. And that was an intentional design that we did to make sure that if you get a hardware acceleration here, you also get a hardware acceleration there. But those are the three main circuits that we have architected.
I want to come back to proof of succinct work in a bit, but we actually have a bunch of questions that I think we should dive into. So Mikera asked, how does Aleo compare with other solutions like Secret Network on Cosmos?
So I'd say what Aleo tries to achieve is a quite broad scope, but in practice, the goal here is really to target, frankly, usage from other L1s into one shielded pool. I think one of the ways to think about it really is that there's a lot of people who understand privacy now, are interested in it, but obviously there's a network effect to privacy. As you know, fragmenting the anonymity set is a huge issue if you want to preserve someone's privacy. And so in our case, we've architected ZEXI as a standalone system that allows us to immediately have all of these applications from different networks, whether they be blockchains, servers, databases, you name it, basically tie into one system. And the goal for that is so that we all can grow one anonymity set together and grow this shielded pool to be as large as possible together.
So Chao is asking for some typical use cases for Aleo. And I know it's still pretty early days, but I'm curious to hear too what the ideas are.
So I alluded to some earlier, and I'd say for crypto natives, the two most interesting and the two most common requests that I've gotten and the team has gotten really has been around dark pools and mixers. To be frank, a lot of people are starting to realize that their assets, on Ethereum aren't really shielded. That every time that if I were to pay you, Anna, and you receive some ETH from me, you also receive my address as part of that, and you can just go on to Etherscan and look up my address and see how much balances I have, how frequently I'm transacting, what apps I like to use, and also potentially other people that I'm transacting with that you recognize. And this is something that people are starting to recognize in their own accounts. And in the normal notion of a bank account, it's almost kind of unheard of to just have that be open. And so this is one area that we've found to be quite impactful. And on the other front, certainly has been with dark pools that with a lot of DEXs and DeFi applications, the nice thing about being public is that everything is public. And so you can see it and validate it. But the downside is also, as we've seen recently with these miner extractable value concerns and discussions, that it also leads to front-running attacks and risks there. Because you can now reorder transactions, you can forego transactions, you can effectively nullify transactions in the sense that a miner who sees an opportunity can stick their own transaction in and game the system. And this is something that ZEXI is uniquely poised to prevent. because the system is fully private. And so I think for crypto natives, the concepts are quite clear that these are two areas that I think are very promising for the technology.
I think generally this idea of DeFi and privacy, that's one of the poll questions that I actually put in originally on the event. I think that's such a important conversation that I hope to actually explore more with subsequent events and stuff like that. Hopefully you can join. All right. Suleiman asked, is it possible to use Aleo and SnarkOS as part of an NPM module logic in browser?
Thank you for asking this. Yes. Well, not yet. But yes, we want to do it. We're working on it. Actually, if you're interested, feel free to ping me, howard@aleo.org. I'd love to discuss it with you. Like, it's something that we've been actively exploring right now because we do want to make it easy to just on the web, frankly. And we have some simple applications we've been piloting internally to try to just see this into something that's mature enough to open source, and would love to brainstorm with you on that.
Asked, why must testnet be trusted?
This is a great question. So, without giving away too much, we will have a setup event coming down the line. It's something that we've spent a lot of time working on. And the reason that the testnet currently is trusted is that we're very early. And so, we want to be kind of transparent or frank with the community that this network was spun up by us. You shouldn't use it to put real money in it. But if you would like to build applications, try building applications and testing it on an open network. It is available for you to use it there. And in the future, we will have a trustless testnet that will be live for you to use.
I see you meant trusted as in trusted versus trustless. Got it.
You shouldn't trust us, and that's part of the technology.
Got it. So Robert was asking, how scalable is the blockchain? And then his subsequent question is, how does the blockchain work? So maybe you can put those together.
Yeah, no, these are great questions. I would say, the framing is very similar to Bitcoin and Ethereum in the sense that you have a mempool and you have a ledger. Frankly, in SnarkOS, we've architected it to be quite modular so that we can support multiple ledgers if your client would like to. And on the other side, the client can also run programs if you'd like to. The goal right now has been to stress test and to benchmark. And because of that, I don't have numbers that I can say right now. But at least in our initial tests, it was easily 100 transactions to 1,000 transactions per block without issues. Verification on that is under 20 milliseconds currently per transaction, and it's a constant time operation. So we feel pretty comfortable that this will scale quite easily to large numbers of users.
Sean asked, ZEXI proposed delegated computation using blind signatures, allowing for mobile processing. Does Leo actually support that? So I guess you meant ZEXI in the original paper.
Yeah, so one of the things that we've been very careful about adhering to is the ZEXI model of delegated compute and also non-delegated compute. We want to make sure that people who are on low-end devices like mobile devices have the ability to call out to either their own hardware or to third-party hardware to run their computations. And frankly, with the inner and the outer circuit, there's also two different levels of running that. So what I mean by that is on a program level, and on the inner circuit level, you may want to run that on your own hardware. But on the outer circuit, because it's effectively like a compression circuit, you can offload that to a third party if you're okay with losing functional privacy, but not data privacy. What that means is that third party would learn what application you used because they see the IDs for the verification keys, but they wouldn't know precisely what information you use the application for. So if it's a payment or if it was an exchange or if it was a message or it doesn't know semantically on that level. And so there's different levels with which you may be interested to offload this. And that delegation model for mobile, I think, will be very important to seeing it kind of happen full-fledged in a mobile app then.
Kev asked, does the Leo abstraction apply any overhead to circuit size in any case?
Yeah, that's also a great question. So yes, there is. And currently what we're doing in Leo is to not toggle that on unless you put in the flag to load state as well. The idea is that there is one small layer of abstraction, which is effectively like two Merkle proof checks. And those abstractions allow you to ensure that this transaction actually lives on-chain for the inner circuit and the outer circuit process when you construct a transaction. Outside of just that one state abstraction, there is no additional overhead. And frankly, the goal with the compiler has been to build a system that is quite optimized while also being provably correct. And there's a lot more that I can talk about that once we kind of push that work along the way.
Dara asked, which proof system is it? I know that ZEXI originally used Groth16.
Yeah, thanks for the question, Dara. So the current architecture has two different proof systems. There is both Groth16 and also Marlin. And in the case of the inner and the outer circuit, we use Groth16 for performance reasons for these transactions. We've actually been evaluating a fallback plan to Marlin so that in case there is a vulnerability in the Groth16 circuits, that our network can also support switching over to Marlin as needed. But for all programs, like Leo programs, and also for consensus, these will be using Marlin. And the goal with that is to have a universal and updatable system that allows us to ensure that things can continue to maintain correctness, but also to make it convenient for the developer experience, that there does not need to be gigabytes of keys stored across the board in order to use different applications, that you could in theory store just one and index it into the respective keys that you need per application.
Ronald was asking, when you say apps run offline off-chain, where do you foresee the end user provers to run? On their own device or in their wallet or on an Aleo provided AWS instance?
So tentatively, we're building one. We want to make it public for everybody, so you can run it anywhere you want. You could run it on a laptop. You can run it on AWS. You could also find a host, and we're also working with a few different teams to try to get people who are interested to actually run this as a service. And if you're interested to run it as a service, like please reach out. Would love to work with you on that front. The goal for us has been to, and personally, one of my personal goals is to just see this technology become commonplace or really commodity, so that you can use it wherever you need to and where you would like to. I think that just access and infrastructure has been such a barrier, and also tooling is also another aspect that has been such a barrier that I think not prioritizing this would be a disservice. And so the goal is to make this all out there for everybody to use, and the hope is that people will go and build different endpoints to actually call into it.
Kev asked, he mentioned that you mentioned that Leo, or JavaScript inspired Leo. Does this mean that some constraints will be implicitly applied?
This is a great question. So everything in Leo, except for console functions currently today, are native circuits. And the reason for using the JavaScript model is that in JavaScript, web developers look at two contexts implicitly, actually. There is, as a React programmer, you might think about writing code that will render in a DOM, and then you might think about code that will print out in a console. Oftentimes when you're debugging and writing a web app, you'll think about it from these two frames almost implicitly, because you're just checking, does it show up on the page itself, or does it show up on the console on the side? And right now, we don't have a very clear model for that within the ZK space. And part of borrowing this notion was that it's quite intuitive that if you replace the word DOM, which is just a tree effectively, with circuit, and it's just a DAG effectively, that you can think about it from that model and separately have your console on the side as well. But also for the use case that we're looking at, which are web applications, it already comes with this two-tone model anyways, that we would want to adhere to that. And so in Leo, effectively, console functions like asserts, console.assert, console.log, these types of methods would only be at compile time. And in the case of the actual rendered circuits, everything else will be baked into the circuit itself.
There's a related question here. Are you concerned about Leo uptake because most devs work in imperative languages and don't understand functional languages?
That's always an uphill battle. And also, like, the definition of functional, at least for my PL friends who are much more eloquent speakers about this than I am, say that it continues to evolve. Frankly, I think that there is an uphill battle. There is also generally a much better abstraction model, which is part of what draws people to the functional languages. And I personally subscribe to that model, that I think it's a good one for this context, because snarks themselves are very modular in terms of gadgets, and gadgets behave like functional units within a programming language.
Francois asked, what are the trust assumptions I need to adopt when using Aleo?
So for one, the goal with putting out the package manager has been to provide a way to publicly see and to publicly check what circuits are being used in an application that you're interacting with. And on the other side of things, I'd say there is also going to be a setup event down the line to make the actual cryptography under the hood effectively trustless for all intents and purposes, so that in terms of what you really have to look out for are these two dimensions. But outside of that, none really come up to off the top of my head, but I believe that these are the two main ones.
There's a lot of great questions. There's some really long ones coming up. So Howard, I think people are very interested. Mikhailo? I don't know.
Maybe we should be doing a Q&A session just on its own.
So Mikhailo asked, are there any limitations to the code being developed, assuming it uses Snark for computation? This means the code cannot be Turing complete. This is actually a question that I had as well about whether it's sort of ZEXI and Snarks are considered kind of, connected somehow. Is that always the case?
So it's a great question. And also, like, to your point about Turing completeness, this is also a great question. There's two dimensions you can look at it on. On the Leo sense of just writing application itself, currently it's not Turing complete. We did have a lot of discussions about whether we wanted to do it. And frankly, we realized, from our perspective, it's best to allow people to write small gadgets if they want small gadgets. And then for people who want Turing completeness in an application, to support basically a VM circuit, so that you can, just like in the TinyRAM model, write Turing complete code. As you may have seen from other teams that are in this field, there has been a lot of explorations on that front, and frankly, our work is quite complementary to theirs, in the sense that we could also adopt very similar approaches, or even work with them to integrate that into Leo. Currently, the approach we've taken has been one for efficiency reasons, to keep things small and to keep things lightweight, and also I think that down the line, if there is demand for having it be a Turing complete system, we certainly will bake in a VM then that has that functionality in it.
So Dara was asking, kind of the continuation, have you thought about other proof systems such as Plonk or Halo?
Yeah, I think that's one that I would say it's such an evolving field. It's very exciting, and I think one of the reasons why we picked Marlin to start was that it's the one that we from our team are most familiar with and comfortable with for universality here. But it doesn't preclude other options. And I think for privacy, it has been a concern that different types of programs may have different verification times or sizes because of the proof system's kind of trade-off for transparency. On the other front, I'd also say that this space is fast moving, and I'm always looking for a better ZKP to use. So if there is a better primitive that comes along the way, I'm very much open to swapping out Marlin for something else. And I think that most on the team would also echo the same thing, that it's just, it's been a huge priority for efficiency's sake, because as you know, with web applications, the demand for kind of instant interactions is quite high. And zero knowledge proofs historically have had a lot of barriers to getting to that performance level.
Mikhailo had a follow-up question to that first question, which was, since Aleo is meant for other L1s to use it, are there possibly going to be bridges to Aleo, or would it possibly compile, say, EVM bytecode or to Snark OS bytecode?
Yeah, no, it's a great question. And frankly, like, I know that there's a lot of teams that have looked at interoperability. I think that with a lot of approaches, there has been a top-down approach of running light clients. And I would say for us, it likely won't be much different. Right now, it's a bit early for us to really engage on L1 discussions. And so, in terms of bridges, yes, but also very curious to see where the approach evolves. Like with teams like Coda doing succinct blockchains, I think it's very interesting or intriguing to have a simple proof that could check and attest to the validity of a transaction in a block without having to run a full light client to verify that this exists and effectively use consensus in that mechanism. Oh, are you muted there, Anna?
Sorry, yeah, I muted myself.
Oh, there we go. I can hear you now.
Mina, what I said, I just corrected you because you said Coda, but it's Mina now.
Mina, my bad.
Yeah.
Sorry, Isaac.
Okay, Zach Williams asked a big, long question that I'm going to try to do justice to. So does Aleo architecture have a concept of call semantics? For example, if one creates a circuit that creates shielded tokens, is it possible for a third party to create a decentralized exchange that instructs the former circuit to update records on behalf of the user? I'm going to leave it there. You guys can read the rest of the question.
The answer is out of the box, no. But if architected, yes. And it's a package that we've been working on to do this like effectively hyper-threading model. You can call one into the other, and we have something called program registers that's an addition to the original ZEXI model that allows you to pass state between these records within a transaction, so that you can execute without having to make a trust assumption about like the model that you're operating in, and so you can keep that boundary between a third-party token and your application. It's something that I'm also happy to walk you through in detail as well, just one-on-one.
Kev asked, can you go more into the detail of the compiler architecture? Is it fairly stable, or will you switch it to something?
I would say there's a diagram that we've been working on that we're going to put in the repo very soon. So stay tuned. But there's multi-passes, and we've been doing a pretty large compiler architecture upgrade as of the past 30 days. There is a pull request you can track that has that, and it also has the diagram in there. Actually, I think we did put it up. Maybe I can just link it in here right now to save time. But the effective model has been to parse everything into an AST, then do type resolution on it, then do optimizations on that. So for example, constant folding and these types of functions where you know that you know the kind of semantic or state about an application, and you can then parse through that, and finally circuit synthesis. But let me paste the architecture into the chat here, because I believe it is up here. I'll need to find it. Apologies. Oh, Anna, I can't hear you.
I'm using my mute too well. Okay, I wanted to ask, Kev had a follow-up question to this, where he said, I asked because proof creation times with a programming language would become compilation time plus prover time. This is going into the compiler, like following up on the compiler question, I believe.
So in terms of the compiler times, it would be the proof time. And the compiler itself is quite quick. Like for most applications that we've been playing with, it's usually seconds. I think the longest I've gone was something that was close to, gosh, like maybe 2 to the 19 or 2 to the 20, if I remember right. And like it was on the order of like 3 or 4 minutes. This was also on a very beefy MacBook Pro. And so, depending on your hardware and your laptop or desktop setting, the compiler performance will vary as well. We've tried our best to keep things as parallelized as we can, but there's also a lot of work we can do to use async to prioritize certain things so that the compilation path itself is faster. Always looking for devs to work on that. So if you're interested, would love to debrief with you on that.
Awesome. So there's a couple, I think there's a couple more questions. Actually, people are answering the questions in the chat, so that's awesome. But I would put, if you do have any sort of last questions, maybe put them in the chat now, because we only have 15 minutes left on this block. And yeah, there's one more from Kev, which was, do you envision a situation where the package manager becomes an attack vector?
Yes. Yes.
Are you worried
I
about
need
that?
to write like a post somewhere so that there's an open discussion about this. Basically, in its current form, it can be an attack vector. Leo itself also assumes the package manager to be this one package manager. In reality, the goal is to modularize that to be whichever manager you'd like to use. And as part of that, we've been exploring an on-chain circuit registry so that you can publish this directly to a ledger itself, in this case, SnarkOS. And this way, there is a more resilient repository for everybody to host their circuits on. But in practice, right now, we do rely on the package manager and exploring a compact and a succinct representation for storing those circuits on-chain.
And I think there's one last one that I can see here, which is, can you elaborate on the Leo compiler performance when the circuit size is above 2 to the power of 20?
I actually don't have a lot of data points beyond 2 to the 20 right now, but if you're interested to write one that is that big, like, I'd love to work with you on it, or feel free to publish it and to ping me, because I would love to see the results myself.
Very cool. So I guess as a last question, if there aren't any more in the group, where should people meet you, find out more? What should they do to get involved?
Yeah, I'd say first off, there's a QR code on the screen for the developer docs. I would highly recommend you check it out. It gives a lot of the basic concepts that I talked about today here in depth. On the other front, if you're interested for the Leo compiler, if you go to leo-lang.org, it's a redirect to the GitHub repo for the Leo compiler. And also, if you go to snarkos.org, it's a redirect to the GitHub repo for snarkos. Feel free to check those out, and also star them if you like it. On the other front, I'd say, like, if you're interested to try writing an application, if you go to aleo.studio as the URL, you can download Aleo Studio today. It has Leo built in, batteries included, and you can start writing an application right from the IDE that we've been working on.
Very cool. So thanks so much, Howard, for the talk, for the Q&A, almost like a fireside chat.
Thanks for hosting me, and thanks for having me. I really appreciate it, Anna.
Cool. So we're going to sign off from this stage. Oh, I'm supposed to look up here. We're going to sign off from this stage for about 10 minutes, and then we should be back with Pratyush talking about ArcWorks. Exciting. Cool. See you soon.
Yay.